Hello.
Yes, sir, you are audible, sir.
Yes, sir.
Okay, okay. Now, can you see this presentation? This whiteboard?
Yes, sir.
Okay, okay. Today I will discuss about the classifications of discrete time signals. Let us uh, write the topic. Classification of discrete time signals. Now let us classify based on energy and power content of the signal. Number one, based on energy characteristics and power characteristics, we can classify the signal, discrete time signal, into two classes: energy signals and power signals. Okay. Now, for discrete time signal, suppose the discrete time signal is given. Xn is the discrete time signal. Okay. Now we can calculate the energy of this Xn. This energy actually total energy. You can write here, sorry, the total energy of the signal Xn is given by E, and this E is equal to summation n is equal to minus infinite to plus infinite Xn mod square. This is the equation. Okay. So suppose you have some signal like this. This is the definition of total energy. Okay. Suppose you have a signal, discrete time signal, which is like this. Suppose this is one SIPS. This is another sample. This is another sample. And this is another sample. So suppose we have 4 samples. This is Xn, and this horizontal axis is n, representing n. And for other values of n, both this is origin. Okay. For other values of n in both sides, right hand and left hand side, with respect to the vertical axis, this is 0. Only we have 4 samples. Okay. This is n is equal to minus 1. This is n is equal to 0. This is n is equal to, suppose, 1. This is 2. This is 0. Okay. So here, if you want to calculate the energy for this signal, and suppose this value is 2, this value is 1, this value is suppose 0.5, and this value is suppose again 1. Then the total energy will be here summation. Here equation is this mod Xn square, and n is equal to here minus 1 to 2 actually. Because for other values of n it is 0. So if you write, then if you sum up this, perform the summation here, then it will be 2 square plus 1 square plus 0.5 whole square plus 1 square. This is the result. So you just, here it is equal to 4 plus 1, 5, 5 plus 8.25, Okay, 5.25 plus 1, 6.25. So result will be 6.25. This is the energy. And if the unit is given here, then you can give the energy. It may be in joule if the values are given in voltage, something like that. So energy can be calculated by using this. Okay. Now, similarly, you can find out the power also. Now, you have to remember that this energy, if you see that this energy E, yeah, maintain this equation, then it is called, did I discuss this? Most probably.
Yes, sir. You discussed a part of this last class, sir.
Okay. So this is your, if this relation is means holds good, then the signal is called energy signal. That means here the total energy is finite and non-zero. So if you see that the total energy of a signal xn is finite and non-zero, then that signal will be obviously energy signal. Similarly, you can find out the average power of the signal. Average power of a signal xn can be computed by, yeah, I am writing here, P is the average signal. Suppose this P is equal to limit, for example, capital N tends to infinity, 1 divided by 2n plus 1 summation n is equal to minus capital N to capital N mod xn square. So this is the equation for calculating the average power. Now once again, here you see how many sample values you are taking for finding the average value. You are taking 2n plus 1 number of samples. That's why after means adding all these sample values, squaring the sample values, then here for this part you are getting the energy for those samples. And then you are dividing this by time. Time means here number of samples. Okay, number of samples. Then it will give you the average power. Okay. So here you are taking minus n to n. So 2n plus 1 number of samples you are taking. So in the left hand side minus n, then the right hand side plus n. So 2n, and at n is equal to 0, at small n is equal to 0, another sample is there. And therefore the total number of samples is equal to 2n plus 1. And you are getting the average power by if you perform this equation. Okay. Now, so what you can see, if you consider that En is equal to, suppose for example, small n is equal to minus n to minus capital N to plus capital N mod xn square. So suppose I am writing this as the this as energy, because you know capital N here. Now I am taking capital N in place of minus infinite. So you are taking the energy content for 2n plus 1 number of sample values. Okay. So what I can write, uh, if capital ends to 10 infinity, then you will get E, total energy. Okay. Because here in our last equation, what is summation? We wrote this summation xn mod xn square. Okay, n is equal to minus infinity to plus infinity. This is your E. I don't know in the last equation whether I have given this n equal to minus infinity to plus infinity, this limit. If I did not give that, then you please put. Okay, so this is our E. Now since this is our E, so if you take n tends to infinity, then I can write that limit n tends to infinity, E n is equal to actually E. Okay. This is actually. So then what we can write based on these two equations, I can write this, that the average power P can be written in this form, capital N to infinity, En divided by 2n plus 1. Okay. Now you see that if E is finite, then obviously P will be equal to 0. On the other hand, if E is infinite, then the average power P is then the average power P may be either, I can write here, may be either finite or infinite. And if P is finite and non-zero, the signal is called, I'm ready, the signal is called power signal. That means here again, once again, I am writing this condition. A signal will be power signal if this condition is satisfied. That is, P is finite. Now, from this discussion, what we can observe, we observe that if a signal is energy signal, it cannot be power signal, because suppose for energy signal, U will be finite. And if E is finite, then P will be 0. And if P is 0, then it will not be power signal. That means E finite means energy signal. When a signal is energy signal, then obviously power will be 0, and consequently it cannot be power signal. So a signal cannot be energy signal and power signal simultaneously. Okay. So this is our energy signal and power signal. Now, next part is this next classification will be done based on periodicity. So number 2, periodic signal and aperiodic signal. Already I have discussed about the definition and classification of periodic signals and aperiodic signals for continuous time signals. Okay, but here for discrete time signals, just I have given idea for discrete time signals also. A signal xn will be periodic if xn plus capital N is equal to n for n greater than 0. N should not be 0. Okay. So this is capital N. Sorry. That is capital N greater than 0. Okay. And here I can write for all n. Also, this n is your lowercase n. Okay. And the smallest value of capital N is called the period of the signal. Or the signal. Okay. So this is the definition of power periodic signal. And if you see that this xn plus capital N is not maintaining this xn, then I will call that the signal is that this signal is aperiodic signal. Okay. And I also told you that a signal, sinusoidal signal in this form, suppose I have a sinusoidal signal xn in this form, xn is equal to a sine twice pi, suppose f0 into n. Now, this signal, this sinusoidal signal or xn will be periodic even only if f0 is what? A rational number. F0 is equal to k divided by n. If f0 can be written in this form where k is integer and n, capital N is also another integer. That means f0 should be rational. When f0 is rational, then only I can say that this particular signal is periodic. Otherwise, it is not periodic. Okay. Now, next classification is done based on means whether the signal is odd signal or even signal. So I will classify this signal as number 1. Number 3, symmetric and antisymmetric signal. This symmetric signal I am writing here. Suppose symmetric signal here it is even signal. Okay, then and antisymmetric signal. This antisymmetric signal here also I can write odd signal. So this will be odd signal. So I write here odd signal. Okay, just 1 minute. Let me. একদম কথা যেন শুনতে না পাই ক্লাস হচ্ছে। So antisymmetric signal, symmetric signal and antisymmetric signal. Okay. Now, all of you know that if xn is a signal and if you see that x of minus n is equal to xn, then I will say that this is symmetric signal. Okay, a signal will be symmetric. A signal xn will be symmetric if this condition is satisfied. And if you see that x of minus n is equal to minus xn, then it will be antisymmetric signal. Okay. So no, this is even function, this is also odd function. Okay. And for antisymmetric signal, for this antisymmetric signal, x0 will be always 0. Just you will see that for any kind of antisymmetric signal, the sample value or signal value at n is equal to 0 will be always 0. But it is not, it may not be always true for a symmetric signal. For symmetric signal, sometimes it may be, but sometimes it may not be. I don't know. Okay. So here you have to remember this particular point. Sometimes it is means used for calculating the energy or signal power. Okay. Now here, if a signal xn is given, suppose the signal xn is given, then it is possible to find out the even part of the signal and odd part of the signal. Any signal xn consists of even part of the signal and odd part of the signal. That means I want to say any signal xn can be written as xen plus xon, where xen is the even part of the signal and xon is the odd part of the signal. So this is odd part of the signal. Okay. Now let us try to find out what should be the expression for xen and what should be the expression for xon. I will try to find out this.
Sir, could you
Okay.
explain again, sir, why is one function equal to the composition of even part and odd part, sir? So I didn't get that part, sir.
Huh?
Sir, I didn't get why. How are we coming to the expression of xn equal to xen plus xon, sir?
I will show this. I
Okay,
will
sir.
show this. There is a proof, obviously. That's why I am writing. I will show it. Okay. So initially I am telling that that xn can be written, any kind of function xn can be written as a summation of even part and odd part. Then I will try to find out the expression for even part and odd part. Then I will add this. Then you will see that it will give you xn. Let us see. Suppose I have a signal xn. Okay. Now, if you assign even part x en as this, suppose this is equal to half x n plus x of minus. Then xn will means it will be equal to xn for this. It will be equal to xn because x of xn, x of minus n is equal to here xn. So you see half xn plus xn. So it will give you, by this operation xn will assign this xn. Okay. So I can write xn in this form. Again, xon can be written in this form, xn minus x of minus n. Here you see x of minus n is equal to minus xn. So if you put minus xn here, it will be minus minus plus, then xn, 2xn divided by 2, it will give you. So since you are putting this condition in this case, therefore it will give you xn. Okay. Similarly for this even function also. Now you see, if you add these two, then what you are getting? So xen plus xon. And this equal to, you see, half xn আমার ক্লাস চলছে, আমি পরে বলবো। প্লাস half x of minus n plus half xn minus half x of minus n. Okay, now you just cancel these two because plus minus sign is there. So half xn plus half xn means xn. So you can write xn is equal to xen plus xon. Okay. Now this is actually proved. Now next I will try to do some manipulation on the discrete time signals. So what will be the next topic? Simple manipulations of discrete time signals. Okay. Now the manipulation can be done on the dependent variable or on the independent variable. Okay. You can say that this manipulation is nothing but a transformation. Okay. So here, if you want to manipulate a signal on the time variable n, time variable is n here. Suppose the signal is xn, then this n is the independent variable. And this xn is the dependent variable. Okay. Therefore, the manipulations can be done either on n or on xn. Okay. Now, what are the different types of manipulation you can do on this independent variable n or time variable n? N is the time variable, which is independent variable. Okay. Let us see how to do that. Suppose I have a signal xn, then I can add some constant term on n. Suppose xn plus 2. So what kind of manipulation? Or you can subtract some constant value from xn, xn minus 2. Then what will be the effect on the signal? Actually, this operation is nothing but a time delay operation or shifting operation. Just what you are doing, you are shifting the signal either at the right hand side of the vertical axis or at the left hand side of the vertical axis. For example, here, suppose I have a signal xn is like xn, and the xn is this. I am just showing the graph of xn. Suppose this is one sample value. Suppose this is another sample value. And let us consider this is another sample value. I am taking this signal xn. This is 0, this is 1, this is 2, and horizontal axis is n. Okay. Now, if you want to perform transformation or manipulation on the independent variable n in this way, by writing n plus 2 in place of n, then what we'll see that at n is equal to 0, original value for original signal it was x0, and here it will be x2, because if you put n is equal to 0 here, then obviously what value you are getting here, x2. So at n is equal to 0, this particular value, let me here sorry, let me erase this. I want to draw this axis using black color. So now here this sample value will appear at n is equal to 0. Then this sample value will appear at this n is equal to minus 1. I am writing here this sample value. And this sample value, which was at n is equal to 0 for xn, this will appear here at n is equal to minus 2. So minus 2, minus 1, 0. So the same signal shape we are getting here, but the signal is shifted here to the left hand side with respect to the vertical axis. And how many samples are delayed here or advanced? There's 2 samples shifting the left hand side. Similarly, for this second case, xn minus 2, you will get what you will get 2 samples delay. Therefore, this sample of xn which is at 0, this particular sample, this will appear here at 2. Then this second sample of xn, this will appear here n is equal to 3. And this sample which was at n is equal to 2 in xn, this will appear at n is equal to 4. So it will be 2, 3, and 4. Because why? Can you tell me? Because you see, when you put n is equal to 4 here, then you are getting x2. And what is x2? x2 is this. This is x2. x2 is this signal. So this is x2. So when you are putting n is equal to 4 in this particular signal, then you are getting this signal x is equal to this value here. Similarly, for n is equal to 3, you are getting x1. x1 is this, and this x1 will be shifted here at n is equal to 3 for this signal. So this signal is xn minus 2, and this signal is xn plus 2. Okay, this is nothing but a shifting of the signal, keeping the shape of the signal same. Signal shape is same, but thus the signal is translated only along n axis, either at the right hand side of the vertical line or towards the left hand side of the vertical axis. Okay, so this is our shifting operation. Sometimes it is called time delay operation. Okay, another operation is called folding operation. Number 2. So previous one was time delay operation, and the second is your folding operation. Folding operation. This is also one operation or transformation on the time variable. Suppose you have a signal xn. Okay. Then if you perform folding operation on this particular signal xn, the new signal will be x of minus n. It is a time reversal signal. So after folding operation, whatever signal you will get, that is time reversal signal. Now you can ask what should be the shape of the signal, what should be the effect of the signal. Here the signal just this will produce, if you have the shape of the signal, suppose xn, and this x of minus n will be mirror image with respect to the vertical axis. Just I will give you one example. Let us consider a signal is this xn. Just I am drawing the same signal xn. Suppose this is the signal. This is the first sample, this is the second sample, and this is the third sample. This is for n is equal to 0, n is equal to 1, n is equal to 2, and this is n. And suppose this is your xn. Then after folding operation, just you will get, the folded signal means actually it will give you the mirror reflection or mirror image of the signal with respect to the vertical axis. Then what we will get? Here at n is equal to 0, the same value will be there. But this particular sample value will appear here -1. It is 0. And this second sample x2, this will appear here. So this signal is now x of -1. This is n. Now you see this particular signal is the mirror. This is 2. Okay, -2, and this is -1. This is mirror image of this signal with respect to the vertical axis. Sometimes it is called folded signal. Folded signal. Folded signal. Okay. So this is folding operation. Clear? Now another operation is there that is also very important operation which can be done on the time variable or independent variable. Just I am writing this number 3, scaling operation. Scaling in time. If the signal is spatial signal, then it will be scaling in spatial domain. Just for example, you can think about one image. Image is a 2-dimensional spatial signal. Okay, so in that case, if you perform scaling in spatial domain in independent variables, then it will give you the scaling of the signal in spatial domain. Okay, And I will show what will be the effect for that operation. First, you try to understand if you perform scaling operation in time, then what will be the real form of the signal. Suppose xn is given. Okay. This xn is given, and the scaling operation here is nothing but a multiplication of a constant term with the time variable. Suppose x2n. So originally in original signal, the variable, the independent variable was n, but when I am scaling that signal, I can scale it by multiplying a constant term. In general, you can write in this form xan, where a is an integer, or it can be any real also. It is you want to say this is ideally this is any real number, but in most of the cases in our signal processing, we will use a constant term a, which is actually integer. Okay. So here, if a is equal to 2, then this will be your scaled signal, scaled in time. Okay. Now, what will be the shape of the scaling signal, scaled signal? You can see this just by considering a signal xn here. Arbitrarily, I am considering a signal. For example, this is the signal. This is, suppose this value is 1. Suppose this value is again 1. And this value is suppose 0.5. This value is suppose again 0.5. Just I am taking a signal. Another two signals I am taking just to understand. Suppose this is 0.25 and this is also 0.25. A signal is like this. This is n is equal to 0. For n is equal to 0, n is equal to 1. Here 2, 3, 4, 5. So how many samples are there? 6 samples are there. Okay. Now, if you perform this scaling operation by multiplying a constant term 2 with this n, so the signal will be now x2n. Okay. Now, what will be the shape of the signal x2n? Let us try to understand. This is n, this is x. Suppose x2n I am writing. Okay. Now, if for this, here, suppose n is equal to 0. So n is equal to 0 means actually xn is equal to 0. Sorry, xn is equal to x0 and x2n, this is also x0. No problem. When n is equal to 0. For n is equal to 0. I am writing here for n is equal to 0. Okay. So for n is equal to 0, here for n is equal to 0, n is equal to 0 here. Okay. Now at this point, x0 is the value. So x0 is this much. Value is suppose 1. So just I am drawing this sample here. Okay. This is the sample. And then suppose n is equal to 1. Then for n is equal to 1, I am writing here. For n is equal to 1, this x2n is equal to actually x2. Here you are putting n is equal to 1 at this place, so it will be x2. So x2 is this sample value. This sample value is x2 now. x2. So this x2 will appear for n is equal to 1. So at this point, you will get this sample value. This sample value will appear here at n is equal to 1. And here for n is equal to suppose 2. For n is equal to 2, x2n is equal to x4. So for n is equal to 2, at n is equal to 2 here, for n is equal to 2, n is equal to 2 here, At this point, what will be the value of this? This one. So this value will come here. And for n is equal to 3, x2n is equal to x6. And there is no value x6 because the signal is extended up to x5. So you can say that x is equal to 0 because I am considering the other values as 0. So next value will be 0 and next it will continue like this. So original signal xn was this, and if you perform this scaling operation, then what you are getting? You are getting a signal like this. So this is the effect of scaling. That means actually you are reducing the number of samples, or you are what I can say that you are just compressing the signal in time. You are reducing the number of samples. Okay, so this is scaling in time. Acha, aaj ke hi thak, today up to this much. Okay, I will discuss about the manipulations or operations on amplitude part of the discrete time signal in the next class. Thank you. If you face any question, any problem, please you ask me. Okay. Don't be hesitant to ask. Okay.
Okay, sir.
I am leaving now.
Thank